This is the first in a series of probably what's going to be 3 videos about section 1.7. The word up there is pronounced bifurcations, not bifurcations or bifurcations, but bifurcations. In chapter 1, it's bifurcations for the kinds of differential equations we've been considering, where you've got a first order equation in a scalar dependent variable. There are other more complicated kinds of bifurcations, but we need to be able to handle these, the simplest case first. I'm going to write down a differential equation. dy dt equals negative y squared plus 2y plus, I'm not going to put a number and I'm not going to put a y next. Instead, I'm going to put another letter. I'm going to use a Greek letter. I'm going to call it mu. Mu is an example of something that you've read about. It's an example of a parameter. What is a parameter? Well, let's first review what variables are. T is the independent variable. It's, in a sense, the ultimate independent variable. Nobody can really affect how time moves. And y is the dependent variable. Y depends on t. The goal is to determine how y is related to t based on this differential equation, which governs how y is related to t. Mu, well, I suppose we could call it a variable, but the standard thing to call it is a parameter. It's something that's kind of independent of t and y. Typically, we don't think of it as depending on t, but we might be able to change it in an experimental situation by changing the conditions of the experiment. For example, if we were experimenting with a mass on a spring, we might change the size of the mass. Or if we were gathering data about the relationship between foxes and rabbits, how can we change a parameter there? Well, we might change the environment that they're in. Those are different ways that parameters can be changed. When you think about this differential equation with the parameter in there, initially you want to think of the parameter as constant. You want to, for example, imagine solving this equation with the mu as a constant. But the most interesting thing to do after you've done that is to think about what happens as mu changes. So in a sense, it's a constant that later on we will allow to change. And the main thing we're after is trying to figure out whether there are sort of rough qualitative changes in the phase line for this differential equation as mu changes. We're not so concerned with minute quantitative changes like changes in the slope of the slope field marks as mu changes. Rather, we're interested in rough qualitative changes. For example, do the number of equilibrium points change as mu changes? So how should we go about this? Well, the usual thing to do here, whether there's a parameter in there or not, when you're thinking about phase lines, is to try to find the equilibria, if there are any. This is a quadratic function on the right-hand side. Let's set that right-hand side equal to 0 in order to find the equilibrium points, which again are going to correspond to equilibrium solutions. And well, since you don't know mu, you're not going to be able to factor that. If we had a specific number for mu, we might be able to factor it, but in this case we don't. We have to rely on the quadratic formula. So I'll do my little song and dance. Me, 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 me. I guess it's a y this time instead of an x, but I'll say y is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, that's probably the last time I'm going to sing that. But, if you want a personal demonstration in my office, if you can't remember the quadratic formula, you can stop on by. negative b, the 2 is b, plus or minus the square root of b squared, 2 squared is 4, minus 4ac, in other words, 4 times the coefficient of the quadratic term, the square, and the c is the constant term, that's mu in this case. All over 2a, all over 2 times negative 1. Those are going to be your roots. Let's simplify it. Negative 2 plus or minus square root of 4 plus 4 mu over negative 2. And let's split this up. Negative 2 divided by negative 2 is positive 1. Plus or minus, I could factor a 4 out of here. What I'm doing now is just cosmetic. It's not necessary. I've got the square root of that. I can take the square root of 4 out separately as a 2, like this. And, well, yeah, I've got a negative sign down there, but because of the plus or minus sign here, it really doesn't matter. I can make it a positive 2 there. Maybe I'd prefer making a minus plus instead of a plus minus, but I wouldn't mark it as wrong if you did this. There are 2 roots, are 2 equilibrium points. If mu is fixed at a value that makes 1 plus mu greater than 0. If, however, mu is negative, or 1 plus mu is negative, then we would get a square root of a negative number. That's an imaginary number. And while we'll have plenty of fun with imaginary numbers when we get to chapter 3, in chapter 1, we basically avoid them. If we get a non-real number there, since we're focused on the real number line, we're going to ignore imaginary roots. So for us, it's as if there is no root when 1 plus mu is less than 0. If 1 plus mu equals 0, then there's exactly 1 root. What you want to do now is you really want to draw the phase line for the differential equation many times over for different values of mu. Let's just pick a couple specific values of mu and see what happens. So I'm going to draw a bunch of different phase lines. Let's start at mu equals negative 3. What would the phase line of the differential equation look like when mu is negative 3? Well, when mu is negative 3, 1 plus mu is negative 2. We don't want an imaginary root here. For us, there are no real roots. There are no equilibria when mu is negative 3. So what's going on? What does the phase line look like? Well, it is still there. There are no equilibrium points on it, so you don't mark off any points. Do we need any arrows? Yeah, you do want to put arrows. Should they go up or down? Well, you need to think about what the graph of this function on the right-hand side looks like when mu is negative 3. Using your knowledge about the fact that graphs of quadratic functions are parabolas, and if the leading coefficient of the squared term is negative, they're going to be parabolas opening downward. We know it is going to be a parabola opening downward. You could get your calculator out and graph it. You could plug in mu equals negative 3 and graph it. Let's see if we can do it without a calculator. If mu is negative 3, that's going to mean the vertical intercept is going to be down at negative 3. Here's a little trick. Since that coefficient there of y is positive 2, that's telling you the slope of the graph at y equals 0 is positive 2. That number, the coefficient of the y term, is going to be the same as the slope when y is 0. If you don't believe it, take the derivative of this function. Ignore the differential equation. Just think about that as a function of y. Take the derivative of it with respect to y. You would get negative 2y plus 2. Plug in y equals 0, you're going to get 2 for the slope when y equals 0. Moreover, you could also figure out where the maximum is, where the vertex is. by setting that derivative equal to 0 and solving for y, negative 2y plus 2, set equal to 0, solve for y, you'll get y equals 1 is where the vertex is. How high is the vertex? Well, you'd have to plug in y equals 1 here. We would get negative 1 plus 2 is positive 1, but then minus 3 is negative 2. So this is negative 3 here, this is 1 here, and this is negative 2. The vertex is going to be here. The graph of the right-hand side of the differential equation when mu equals 3 looks like that. There's a mistake in there that I never fixed. In the entire rest of the video, I should have labeled that graph with mu equals negative 3, not mu equals positive 3. It's always negative. So thinking back in terms of differential equations, that's going to tell you dy dt is always negative. So solution curves will always be decreasing, and you'll get downward pointing arrows here. You can draw more than one if you like. The point is, all solutions are going to be decreasing. If we imagine points on this phase line is actually moving in time, you pick an initial condition, it's going to move downwards. The state of the system, if this is modeling some real-life situation, is that the value of y is going to always decrease. Well, let's try y equals, or mu equals negative 1. Looking at this, you might think that could be an important value of mu. And indeed it is. When mu is negative 1, this is 0. 1 plus or minus 0 only gives you one real root. We'll have one equilibrium point when mu is negative 1. One equilibrium point at y equals 1. This would be y equals 1 right there. And that'll be your only equilibrium point. What about the arrows? What direction will they point? Think about what's going to happen up here. As mu increases from negative 3 to negative 1, what's going to happen to this graph? You should realize from your pre-calculus days that adding a bigger constant is going to shift your graph upward. In fact, we're going to take this graph and shift it upward by 2 units, because negative 1 is 2 units bigger than negative 3. If mu is negative 1, you'll have a vertical intercept of negative 1 right there. The vertex will still occur at y equals 1, but now that vertex will just cross that horizontal axis right there. I think I'm having too much fun with these warnings. That vertex doesn't cross the horizontal axis, it just touches it. The whole graph from the preceding example gets shifted up by 2 units. And you can see that except at the one value where this function is 0, everywhere else it's negative. For the differential equation, that's going to mean you're going to have decreasing solutions for initial conditions other than y equals 1. So you want to draw your arrows downward. So y equals 1 would be a node. And that's what your phase line would look like. You should realize that initial conditions starting up here would approach this equilibrium point, but they would never reach it. They would approach it asymptotically as t goes to infinity. The limit would be y equals 1. Initial conditions down here would decrease and probably speed up. They definitely would speed up. And you'd have your solutions going off to minus infinity as t goes to plus infinity. All right, one more example. Let's try mu equals positive 1. Mu equals positive 1. gives you two equilibrium points. One at 1 plus square root of 2 and the other at 1 minus square root of 2. Square root of 2 is about 1.4, so 1 plus square root of 2 is going to be about 2.4. And 1 minus square root of 2 is going to be about negative 0.4. Those will be your two equilibrium points when mu is 1. Going back up to the graph, when mu is 1, we have increased mu by 2 more units. So once again, our graph, because of the way mu is situated in this equation, shifts upward by 2 units. If mu were somewhere else, like in front of the y, say, or something like that, it's not such a simple relationship between increasing values of mu and how the graph changes. But because we're adding mu, it's going to be a simple upward shift. Your two equilibria, again, are 1 plus square root of 2 and 1 minus square root of 2. In between, you see that the graph of the right-hand side is positive. So solution curves increase for initial conditions between those two equilibria. And elsewhere, the graph was negative. So up here and down at the bottom, solution curves decrease. As mu changes, here's the big idea. As mu changes from -3 upward, and certainly once you get to +1, a big change has occurred. Two equilibria have bifurcated, is what people say. Two equilibria have bifurcated from a situation with no equilibria to 1 to 2. Actually, this 1 is going to occur sort of instantaneously at just one instant in time, if you will, if you're imagining mu as being time. The normal, ordinary state is going to be either no equilibria or 2. That's the origin of the name bifurcation, is that you've got these two equilibria sort of appearing out of nothing. Not all bifurcations work that way, but lots of them do, and thus the name has stuck. I want to spend the last few minutes here before I show you something kind of neat, just thinking about this in a little bit more sophisticated way. So once again, here's my differential equation. Same equation as before. And the equilibria, the equilibrium points, we're at y equals 1 plus or minus square root of 1 plus mu. What I had on the previous slide was a crude example of what's called a bifurcation diagram. I'm going to make another bifurcation diagram here, but I'm going to be a little bit more sophisticated about it. I'm going to, once again, in a sense, think of this as a picture of a bunch of phase lines. And I'm going to put a horizontal axis in it, representing a mu axis, representing how mu changes. I'm going to put a y-axis in here, although you should realize that this, in a sense, won't be the only y-axis. This is the y-axis corresponding to mu equals 0. But I'm going to draw, ultimately, a bunch of phase lines in here. But before I draw the phase lines vertically in this picture, I'm going to draw the graphs of essentially these two functions here. Y is a function of mu. What do the graphs of those functions look like? Well, you can, if you've got your graphing calculator, you can take it out and check that those functions will look like this. y equals 1 plus square root of 1 plus mu is a function whose graph looks like that. And y equals 1 minus square root of 1 plus mu is a function whose graph looks like that. By graphing those two functions, what I've really done is I've made a graph showing how the equilibria of the differential equation depend on mu. And in fact, I'm now going to draw a bunch of phase lines in here. This is illustrating the bifurcation in a little bit more sophisticated way. Over here, when mu was a large negative number, there were no equilibria, all solutions were decreasing. When mu is negative 1, you've got one equilibrium point right there at y equals positive 1. And now as mu increases, you get two equilibria. For example, when mu is 0, your equilibria would be at y equals 0 and y equals 2. And they continue spreading out as mu increases. And in your mind's eye, you want to kind of imagine this as a movie that plays. As mu increases, mu is like the time of your movie, you imagine these lines getting highlighted as you move from left to right, and there are no equilibria. All of a sudden there's one, and then there are two. A bifurcation has occurred. I guess I was just full of mistakes that day. To the right of mu equals negative 1, between the two branches of the parabola, well, I should have put those arrows upward instead of downward, so when you go back to the video, make sure you mentally make the change. Talking about bifurcations and equilibria, two equilibria sort of being created out of nothing, reminds me of another situation where it's as if we're creating something out of nothing. One of my favorite little things to show students, I'm going to take the number 0 and I'm going to create out of this number 0 the number 1. I'm going to create something out of nothing. You ready? 0 equals 0 plus 0 plus 0 plus 0 plus 0, etc. You certainly can't argue with that statement. Well, each of these zeros could be thought of as 1 minus 1. I hope nobody's going to argue that 1 minus 1 is not 0. And by the associative property, I can rearrange these parentheses. I'm going to do it like this. And certainly you can't disagree with me that negative 1 plus 1 equals 0. Therefore, 0 equals 1. And I'll let you chew on that for a while. Once you think you figured out how I did this trick, you can come and tell me what you think.